Software inspections are the second half of our code review, or our list of code review techniques. Software inspections, the goal with the software inspection is essentially to do something like a walkthrough, but in a much more focused, much more procedural fashion, often to detect particular kinds of defects, security defects, privacy issues that may come up. You want to fine-tune an algorithm that has extraordinarily high load or has to be massively concurrent or parallel or any sort of technical detail like that. Essentially, a place where you have to have tons of focused attention on a particular kind or particular set of defects. So you're not solution hunting, you're not doing idiomatic updates to the code. You're not really even all that interested in the educational aspects that you might get from a more informal walkthrough process. And you want to do this in a very non-threatening, explicitly non-threatening fashion. Software inspections, code reviews in general, should never be tied to performance reviews for individual engineers because everybody's going to make mistakes. That's an expected part of the software development process. What you really want are people who are going to be active participants in identifying and fixing those mistakes, and by tying something like this to a code review, or pardon me, to a performance review, you're going to end up having them try and hide their problems, and that's much worse than having people having one more element that you can use as part of a performance review. So typically this formal process is going to include the following, right? First, you want to verify the software actually satisfies the specifications. Essentially, this is the step one validation. Does it actually do what we wanted it to do? Step two, you want to make sure that it conforms to applicable standards, especially in the case that you're talking about security and privacy bugs, because there are lots of very good general standards for secure coding techniques. And privacy techniques as well are coming online. NIST just recently updated the draft version of their privacy recommendations, and I think they're very good. So this is another thing that you could include in a formal software inspection. This is another thing that I think people start to recognize as they get more advanced in their career. Those are the kinds of things that really take software from being like functional, workable to really great, right? The stuff that makes millions of consumers happy rather than the sort of thing that will make tens of thousands of consumers happy. And then the third thing that you're trying to do is identify any kind of a deviation from these standard specifications, any kind of a deviation whatsoever that might end up causing problems down the road. Fourth, you want to collect software engineering data on especially defects and effort, right? Again, when we were doing all the planning stuff very early on, we estimated effort for a lot of these things. In a formal software inspection, you can now start measuring and see like how close to target are we, how long did this module turn out to take us to develop, and so on. And again, you're not looking for idiomatic, stylistic, or alternative implementation approaches. This last one, we're not trying to do that. It's really the first three and sometimes this fourth one that are most important. Okay, so when you are doing a software inspection, you should plan for about 90 minutes to 2 hours. They're somewhat longer than a walkthrough. And it's going to be more formally set up as well. So you'll have an introduction to the meeting. You'll have preparedness criteria, including documents that people will have to read prior to coming to the meeting, code that people will have to read prior to coming to the meeting. The standards, of course, people have to understand prior to coming to the meeting. It's not intended to teach you what the standard is. There's not an educational component to this. It's more everyone is already prepared walking into the room, and we're going to do a serious review of the source code at that moment. Typically, you do that review. That's the bulk of the meeting. You have this review and collection of a defect or a deviation list that you'll end up compiling at the end. And then near the end of the meeting, you're going to make exit decisions for each of those problems, right? Maybe for some of the defects, minor modifications will help you. For some others, you may actually have to re-architect, remodularize, or rework the system in general. But that's the thing you want to decide at the end of the meeting. And then you'll assign responsibilities to the code author, to the owner of the module, or to individual programmers so that the decisions you made can actually be implemented. And then finally, you're going to have some kind of a follow-up. It may not require another meeting, but some kind of a follow-up to verify that all of the stuff you identified, all the stuff that you found and created in your defect list actually does get taken care of. at the end of the day. Now, the most critical thing on this whole list of things you want to do with software inspection is making sure that people have studied this stuff beforehand. You cannot have your engineers go into this meeting without being prepared in advance. It's this step right here. The most critical part is making sure everybody's really well prepared going into the meeting, because otherwise it will be very expensive and you will not get very much out of it. So this data collection part, where we're looking at pardon me, where am I thinking? Yes, where is it? The data collection. Yes, I think this is the part that I was talking about, the data collection. Yeah. Oh, yeah. Anyway, the part where you're actually collecting data that you can use to verify the predictions that you'd made previously. You want to do some categorization for those. You want to at least record some information that will allow for future predictions to be based on real data rather than sort of gut estimates like you may have to do the first time through or the first couple of times through. So one way that you could do this, the way that the textbook introduces that you could do this, is to talk about the type of defect that you found. Is it a problem with standards compliance? Is it a regulatory compliance issue? Is it a security issue, some general functionality issue, user interface, user experience issue, a maintainability issue? Might be tied to some other non-functional type requirements. But classifying the type of defect is very critical, because then when you run into similar kinds of concerns in the future, you'll be able to show how often you see those sorts of defects appear in your organization's source code and how easy they are to fix. Then you want to have some understanding of the class within that type. Is it that you've missed some standards compliance element, or that you tried it but you did it in an incorrect fashion, you implemented it incorrectly? That you had a standard but then applied the wrong part of it to solving the problem at hand? Or maybe you did some implementation that was partially correct, partially incorrect, in some kind of an ambiguous or inconsistent fashion, right? The class of the error itself may be another thing you would want to categorize or collect. And then finally, you could think about the severity. Is it a very serious element that was missing, or just a minor element that was missing? And you could have gradations in between, of sort of like a neutral, moderate, that sort of thing. And there's lots of other things that you can collect, but having at least a defined categorization of the sorts of things that you want to collect for each of the problems that you may have identified in your inspection does make it much more efficient to review this after the fact, or to use it as a large set to pull from when you're making predictions in the future for future projects. And your organization will probably have some kind of a standardized approach for addressing this sort of concern. All right, going back to code review processes, the next one on the list is pair programming. The idea behind this is that you would have two programmers working as a pair at a single computer terminal, right? And one of those programmers is going to have the keyboard and mouse in front of them, and they will be considered the driver. They'll do all of the actual typing of the code into the system, and they will deal with all of the immediate implementation concerns. So what is the variable name that we will use for this particular variable in this particular feature that we're implementing right now? The other programmer, and this is somebody who should be a software engineer programmer at the same level of skill. Often you would rotate roles just to keep people on their toes. But the other person in the pair is the navigator. They don't have a keyboard in front of them. They may have like the standards document or the API documentation or something like that in front of them, but they are actively looking for bigger picture issues, right? Larger concerns with how the feature that's currently being implemented should interact with the rest of the system as a whole. So this is a high-level window on the code, and the driver's taking sort of like a low-level, nitty-gritty window on the code. And there's some other links here that I have that I would very strongly encourage you to check out for more information on this. I particularly like this New Yorker article, which is kind of like showing how two of the Google AI folks use pair programming to ensure that they come up with really good AI implementations for some of their research queries that they're interested in. Jeff Dean and Sanjay Gimawat, both very well-known programmers, and they use pair programming. They talk about it explicitly in this article. Okay, so the next code review technique on the list is complexity analysis. Now, we've talked about this previously, so I'll only briefly mention it here to say that this is where you would actually want to do a complexity analysis, right? So this is essentially a way to calculate software metrics for assigning some kind of rule or number or identifier that characterizes the software, and that is the metric that we're trying to do, whatever that metric is. Now, the complexity metric that we talked about previously with cyclomatic complexity is a part of the testing process. Other examples would include things like lines of code, which is a really bad metric, but it is often used simply because it's very simple to calculate, or function points, which again is also kind of problematic for other reasons, but there isn't really a good list of software metrics. This is an active area of research, and I don't know that anyone's come up with something that is sort of universally regarded as like, oh, this is an excellent metric to use for complexity analysis. There's lots of questions about whether or not software complexity is even really a thing. So, for example, a beginning C programmer that's not all that familiar with numerical analysis may find writing numerical software in C very complex, even though it's actually a pretty well understood domain for software at this point. We've got lots of people working in that area, and this could end up causing more problems than it solves. So it is kind of an interesting area for research. I don't know that it has that big of an impact on most software organizations and implementation, but if you're thinking about code review techniques, especially automated software metrics, software complexity metrics that just happen to be calculated by whatever IDE you have lying around or whatever IDE you're using, this is where you'd want to include them in that process, in the software development process. And then static analysis is our last code review technique. So in static analysis, the idea is that you actually have another program examining the source code itself and then telling you information based on what it finds, right? So typically it's done through some kind of a tool support, usually an IDE. Some goals might be to find dead code. So if your IDE highlights, hey, this function is never reached, or this branch of an if statement is never reached, that's static analysis for you. You may also use a static analyzer to verify a style guide, to enforce a style guide. Linters are a good example of a static analysis tool that's used quite regularly here. Sometimes they're just there to enforce idioms in the programming language, helping programmers who may not be as experienced with the programming language not create code that would be a little bit awkward for somebody who is well versed in the programming language. Those kinds of things. So these are the kinds of tools that most organizations are using at some level, whether they know it or not, simply because they're kind of enabled by default for most text editors and IDEs on the market right now. But this is where they fit procedurally within the SDLC process. And I would also encourage you to try and answer this question. What kind of code review tool is most appropriate for, or what kind of approach to code review, I should say, is most appropriate for the Massey market, and why? I normally would have students get into your project groups and discuss this sort of thing after 3 to 5 minutes. And then we would go through some of the pros and cons of the various techniques as applied to the Massey market. Unfortunately, we can't do that. So I think you should do this on your own, or possibly, if you want to, on the discussion boards for this lecture. And just for reference, the Massey market is available in the slides, so you can play around with this in the slides if you need to. And that will be at the end of this subsection. We'll start moving into documentation as a part of the software development process next.